Alright guys, today we're going to prove that for all n is greater than or equal to 1, the sum of the squares of the first two n positive integers is given by this equation here. And we're going to do this using mathematical
First,
function.
look at the base case of n equals 1. So for n equals 1, the first two n integers are the integers 1 and 2. So the sum of the squares of those is 1 squared plus 2 squared, and we're setting that equal to this. So this simplifies down into 1 plus 4 equals 1 times 3 times 5 all over 3, which simplifies even further into 5 equals 15 over 3, or 5 equals 5.
All right, so for the inductive step, we're gonna set n equal to k, and we're gonna find that this is what follows. And using this, we're gonna be able to prove that k plus 1 holds.
Now to prove that k plus 1 holds, we're going to plug k plus 1 into the equation, and you're going to get this long line here. Now notice that when we have 2 in parentheses k plus 1, it really means 2k plus 2, so we also have to include this extra 2k plus 1 without parentheses squared to get the whole true. After simplifying and isolating this, we're going to get this on the right side, subtracting these two, and because of our inductive step, we know that this is just equal to our original equation with k. So after doing some simplification and foiling all these three, we're going to get 8k cubed plus 30k squared plus 37k plus 15 all over 3. And all I did here was just factor in the squared here, then combine them since they're like terms to get, well, eventually it's going to be minus 8k squared plus 12k plus 5. Okay, so after completing this, because we have a 3 in the denominator, we multiply top and bottom by 3 so we can combine them. And after such, we get 8k cubed plus 6k squared plus k all over 3. And this can be factored out, taking out a k and then doing some reverse foiling to k times 2k plus 1 times 4k plus 1 all over 3, which is exactly equivalent to our original equation, proving this true for k plus 1 and there for all cases.
Okay, today we're going to prove that if n is an integer, then n squared is greater than or equal to n. So we're going to do this using proof by cases. So the first case we're going to be looking at is if n is negative. So for the calculations here, we pull out -1 just to make it a bit clearer. So we have negative n squared is greater than or equal to negative n. And this is the same thing as negative n times negative n is greater than or equal to negative n. So we can divide both sides by negative n, and because we're dividing by a negative number here, we have to flip the sign. So we get negative n is less than or equal to 1. And that's always true, so case 1 checks out.
Similarly, for case 2, where we have n is positive, we're going to do the same thing. You just divide by n, and when you divide both sides by n, you're going to get n is greater than or equal to 1, which is always true for positive integers, making our case 2 right.
For the last case, case 3, we take n is 0, and you just plug it in, and you find that 0 equals 0. So case 3 is true, and therefore we've proven that if n is an integer, n squared is greater or equal to n.